So we're going to start with our first talk of the day. And our next speaker is a seasoned web performance vet. He's done a large amount of writing on his blog. He's had some premier clients over time, and he's given several talks at international conferences on performance. I think it's a shock that his name is CSS Wizardry. I don't know what that's all about. But he's also an avid cyclist. Any cyclists in the room? Yeah? All right. Maybe he'll talk about his $10,000 bike or whatever it is. But here to talk about optimizing the largest contentful paint is Harry Roberts.
Cool, thank you very much. This is a really, really long talk, so I'm just going to dive straight in. The full version of the slides are already online. But I want to talk to you today about site speed, obviously, but a very, very specific subset of site speed. I want to talk all about largest contentful paint, which I presume most of us will know about by now, but for those not aware, it's a relatively new performance metric, coined as part of one of 3 core web vitals by Google. The next sort of 40 minutes are going to be looking at what it is and some kind of unusual implications, some caveats, some gotchas, and then just how to work with LCP to make it fast. I work day by day as a performance consultant, and I generally tend to work with larger clients, and that's because generally larger clients tend to feel the benefits of site speed more than others. But ever since Google's announcement that they're going to take site speed into consideration with their algorithm, with their rankings, I've noticed a far broader, far more diverse spectrum of clients getting in touch, which of course is great for me as a consultant, get to work with a much bigger variety of people. But the Core Web Vitals initiative has really started to put site speed on the map for, like I say, more kind of traditional companies, not the kind of big corporations. This isn't going to be an SEO talk. This is going to be a technical performance talk. But I find the conversation around site speed now has really been changed because of Core Web Vitals. So what is LCP? Like I said, it's a new performance metric, part of one of 3 Core Web Vitals, and it's relatively new, a couple of years old, and it aims to kind of proxy when the most pertinent bit of content was displayed to a user. There's quite a technical definition on screen right now, but basically it's a proxy for how fast was the site visually, how quickly do we get the most important bit of content. Oh no, sorry, not the most important. By definition, the largest. It could not necessarily be the most important. How quickly do we get that on screen? Interestingly, for the Performance.now site, it's a P element, so it could be a text node. On my site, it's an image, but it's actually defined as a background image in CSS. If you look at the Meta website here, we'll see it's an H1, interestingly enough. Again, it's a text node. Don't know about you, but I'd reckon that picture of the guy with the VR headset on is a bit bigger than the H1. It's not actually a picture, that's a video, so that's an interesting caveat we're going to look at shortly. Only certain elements are considered for your LCP candidate, and the choice of element does make a huge difference. Videos aren't considered for your LCP, so if you've got a video on your page, it'll be skipped as an LCP candidate. There's a slight caveat there. That's why on the Meta website, it's flagged as an H1. The reason I wanted to talk specifically about LCP today is it's the one metric that sites seem to struggle with the most. Only sort of half of origins get what we consider a good LCP, and this genuinely fascinates me because, in my opinion, LCP is by far the easiest to monitor, measure, and fix both in the lab and in the field. And it really surprised me that so many websites seem to struggle with LCP. The other 2 metrics, first input delay and CLS, we are not going to look at those at all in this talk, which is handy for me because they're much more complex. We're going to look at LCP. Genuinely, when I see this statistic, it blows my mind because it is so easy to fix, and it's the one that 50% of people are struggling with. 53.7% of origins have a good LCP. So what is good? What even is good? Well, as well as defining the metric, Google defined the thresholds, and the threshold was defined as good would be anything that's 2.5 seconds or quicker. So it's inclusive, 2.5 seconds or faster to get the largest bit of content displayed on screen. Now that 2.5 seconds wasn't just picked out of anywhere. There's a lot of research gone into it, and one of the interesting caveats, one of the interesting sort of restrictions is that Google said this: to confirm that a threshold is achievable, we require that at least 10% of origins currently meet the good standard, the good threshold. What they're basically saying is, if 10% of the web can achieve this, we think you can as well. So it's fairly ambitious, certainly achievable. We're going to learn how to do it in this talk. What this implies, and this is implied, like I'm not saying this is the case, the 2.5 seconds could change. In a few years, if 25% of people get 2.5, I imagine the threshold might be redefined. I've not heard that from anyone at Google. Annie Sullivan's probably in the audience panicking that I've just said that. But it just, I'm inferring that this 10% is going to keep changing, right? Or the threshold could change. So it keeps it ambitious, and I like that. I mentioned this is not an SEO talk, so I'm not going to talk about SEO at all. I think, okay, I'm going to go ahead and say it. I think that LCP and the Core Web Vitals as metrics are really, really nice. My opinions on where they slide into SEO and how they kind of sort of strong arm in the web a little bit, not too keen on it, so we're going to skip over the SEO thing. This isn't going to be an SEO talk. But site speed is more than SEO. So I get a lot of clients getting in touch worried about Core Web Vitals, purely for the ranking sort of factor, which is, it's admirable, and that's something I'll help them fix. But I just want to throw an example out there. This is a really great example, just a kind of just a cool number, really. I was working with a client 2 months ago, and we worked out that a 500 millisecond improvement in LCP would be worth an extra 11.5 million euro a year to them. This is staggering. SEO gets a customer or gets a potential customer onto your site, but it's their experience while they are there that is a predictor of whether they're likely to make a purchase or not. So site speed is way more than just SEO, and I encourage everyone who's worrying about SEO to continue worrying about site speed after that person's landed on your site. That's staggering, right? That's really cool. How do we get to good? The whole point of my talk is getting us to good, getting us to this 2.5 second threshold. My first bit of advice would be to solve everything beforehand. LCP is a milestone timing. It's a sort of culmination of several other preceding steps. Everything on this slide, or combinations of it, some or all of them, are things that lead up to your LCP event. So it makes sense to start optimizing these. It's kind of a subtle thing to get your head around, but you can't really optimize LCP in its own right. LCP is a culmination of everything that's on this slide here. So here's a client I'm about to start working with. This is from Treo, one of my favorite tools of all time ever. This is just a client I'm about to start working with. This is a snapshot of their some of their milestone timings. Now, we've got a 2.5 second budget for LCP. This client's losing 2 seconds of that to time to first byte. They've only left them half a second to deal with the critical path and sort of getting to that LCP candidate. They are way behind schedule here, and you can see that at each point afterwards, they just keep losing time. Alexi, the founder of Treo, and I were talking last night. I particularly love this way of visualizing data because each of these steps is a kind of clue as to where they're losing time. So 2 seconds on the server, well, time to first byte. Time to first byte is a horrible metric. It's got that drawer in the kitchen where it's like, I don't know where to put this thing, so it goes in the drawer with all the other things that I don't know. That's what time to first byte is. It's such a messy thing to try and debug. But time to first byte at 2 seconds and first contentful paint at 3.6, the delta between time to first byte and first contentful paint is, broadly speaking, your critical path. If the first bit of data landed on the device at 2 seconds, but the first bit of data you were able to display was at 3.6, we've got roughly 1.6 seconds of render blocking time there. Very crudely, it's a crude proxy. And then 3.6 to 4.4, that's usually a good proxy that the LCP on this site is going to be an image. If the first contentful paint was 3.6 seconds, and the largest contentful paint was 3.6 seconds, it's a fairly good predictor or indicator that was a text LCP. This site, you can be fairly certain that the LCP is likely to be an image. It's not on this slide right now, but if we were to put first paint and first contentful paint in, and there's a gap between first paint and first contentful, that's likely going to be a web font issue if there's a gap there. We rendered text nodes, but invisibly because we weren't handling text web fonts properly. So basically, solve everything beforehand. Each thing that precedes LTP is an opportunity to improve LTP. The next thing, and this is really, really quite interesting to me, is choose the best element. I mentioned briefly there are a finite list of elements that are considered for your LCP, and the choice does make a difference. This slide is lifted directly from web.dev, no edits, didn't reorder any of this, it's just copied and pasted word for word. These elements are listed in no particular order. Image elements, image in SVG, which is a different thing. Video elements, poster attribute. So video element will not be used, but its poster attribute may be if it's present. Elements with background images and block level, basically text nodes. So if it's not an image type LCP, it could well be a text node. This is presented without comment, and I'm a Google developer expert, which kind of means that I'm sort of somewhat aligned with Google, but they don't, it's really nice, they don't give me a gagging order. I don't have to say nice things. What annoys me about this slide, or this text, it doesn't tell you that some of these are inherently faster and slower. It just tells you that, yeah, you could use one of these. But it doesn't tell you which ones are best, which ones are ideal. Some of these are a bad idea. So start with the easiest one. We love text-based LTPs. Text is faster than images, right? Or at least it should be. If not, you're doing something really wrong. My site is, this is a really good just example of this. My site, the image of me is, it's not a responsive image, because I'm lazy. It's just small enough that it works on mobile and desktop, whatever. So this is the exact same image. This image isn't any bigger or smaller on different screen sizes. On mobile, I can get an LTP of 844 milliseconds, the exact same page with the exact same image, the exact same connection network conditions. As soon as the LTP candidate becomes an image rather than text, we lose about 560 milliseconds there, just because we're using a different candidate. Caveat here is make sure you are handling those web fonts correctly. Make sure you aren't just giving an invisible render of text-based content. This is easier said than done. I want to cover this one very quickly because you can't just redesign all of your sites to not use images as the largest element. It's more likely than not that we are going to be using image-based LTPs, and those are the toughest ones to optimize. The list of potential candidates that web.dev gave us, I just ran the same test for each candidate type, but I did something to trick the browser. I wanted to see, basically, how does the browser handle network contention, different resources in flight. So the demo I made was really quite simple. I've got a synchronous script in the head, and then one of each, well, no, sorry, not one of each, but a test with each candidate type. What I'm trying to do here is deliberately trying to trick the browser. And the reason I'm trying to trick the browser is actually for the use case of background images. I just wanted to prove that CSS is slow and background images are slow. Not CSS is slow, I take that back. And it's not slow anymore, not after yesterday's talk. Background images are slow. In doing this test, I discovered more than I actually intended to. So after running these through web page test, here were the results. Image came in at 3.1 seconds. Oh, by the way, this script I artificially delayed for 2 seconds just to exaggerate the waterfalls. So we're not going to hit 2.5 seconds for any of these tests because I deliberately delayed the script by 2 seconds to exaggerate the waterfall. 3.1 seconds for your image. Image in SVG is the fastest at 2.6. Poster image, virtually identical to image elements. This is a really pleasant surprise. Background image, predictably, for me at least, was the slowest at 4.4 seconds. So there's an inherent difference in which element you choose, and I want to sort of explain why. What I found immediately interesting is that image in SVG was so fast. Like, how? Is there some kind of fast path with images in SVGs? Well, there is a fast path, but it's a bug. If you visualize the data like this, if we visualize it visually, the film strips, you notice that LCP for SVGs is actually getting reported as the text node. This is a bug that keeps flip-flopping. It basically was a bug in 99. It was fixed in 102. It's fixed in 106, but regressed again in 107, I believe. So kind of working to pin this down. When we adjust the data for the actual LCP event, we'll see that now image in SVG slips to be in the second slowest. So it's a fair bit slower. This is easier visualized in waterfalls. Some patterns start to emerge, and I really do hope this is large enough. When we look at the patterns that are emerging, both image and poster, that image is discovered first, discovered before the script, and it's fetched in parallel to the script. The reason it's discovered first is actually just a TCP networks thing. It's not actually inherent in how like LCP is working here. But you'll notice the image is discovered very, very early, fetched in parallel to the script, or with the script, very, very fast. This is what we want to see. Interestingly, for both image in SVG and background image, the LTP candidate is not discovered until after the script is finished, which is a big clue about what the browser is doing here. The whole reason I ran this test with a blocking script in the head was to see if this pattern emerged. And I was not expecting to see it in the case of image in SVG, and we'll look at what's happening shortly. First things first, then, image is good. And statistically, if you look at the HTTP archive, you are going to find that I think it's about 40-something% of origins have an image-based LTP. Statistically, this is the most likely one you're going to encounter. And shouldn't come as a surprise, there's the syntax for an image. Really, really straightforward, beautiful, terse bit of HTML. We love HTML. HTML is super fast. Giving this to a browser is a good idea. Reminders of that waterfall, complete parallelization, image is discovered second. This is healthy. Now, the reason that image is discovered sort of before the script and fetched in parallel to the script is because of something called the preload scanner, and I'm going to go out on a limb and guess I don't need to describe in too much detail to this audience what the preload scanner does, but just have a quick refresher. It was invented by IE8. Obviously, being Microsoft, they had to call it the speculative preparser. Enterprise. Everyone else calls it the preload scanner. Basically, back in the olden days, IE7 kind of era, browsers only had one parser that was responsible for discovering, downloading, and executing resources. Everything became very, very synchronous. If one of those resources was a script, a synchronous script, the discovery of the next resource couldn't happen until the execution of the current resource was finished. The preload scanner was invented, and best guess estimates put global sort of like the web performance improvements around 19% just by the invention of the preload scanner. What it did is it decoupled the discovery of resources to the construction of the DOM, the execution of the page, et cetera, et cetera. It was a secondary, inert, download-only parser that made downloads completely asynchronous. It's in every single modern browser, and developers do not need to do a thing to benefit from it. However, we can shoot ourselves in the foot, and we can inadvertently hide things from the preload scanner, and that's what we're going to look at in the next few slides. Again, it's better visualized in a waterfall. Back in the olden days, if we had a series of synchronous scripts, they would all be discovered like synchronously, like in serial. This was a very slow way of working. That's because the same parser that was running the script was responsible for finding the next one, but it can't find it until it's finished running that script. Really, really slow. The preload scanner was turned on, it was invented, it just appeared, and then all waterfalls automatically started looking like the bottom one for free. This brings me on to image in SVG is bad for performance. Statistically, very unlikely we're even going to encounter this, never mind implement one. The syntax is XML, so we've got to stick those self-closing tags and quotes back in there. Fairly sort of innocuous, fairly simple syntax. But the waterfall looks like this. We've completely lost that parallelization. This is because, it turns out, images in SVG elements are hidden from the preload scanner. I don't know exactly why this is. My guess may be that embedded SVGs are parsed separately to the HTML that contains them. It's a guess. I could be wrong. I don't know how easy it would be to give the preload scanner access to that embedded SVG. But as it stands, elements defined in SVG are hidden from the preload scanner. It means they can't be requested until the moment the primary parser discovers them, which is way too late, because by the time the primary parser discovered it, the browser's ready to render it. Brings me on to poster. Poster is good. This is a really pleasant surprise, because I personally have never, ever, ever implemented a poster attribute, which means like it's just like kind of bias, because I haven't and no one else has, and therefore it wouldn't be optimized. It just came as a really nice surprise that this has been optimized. The poster attribute just lives on the video element, and obviously that is just going to be the placeholder while the video itself is downloading. This is available to the preload scanner. This is fast. This is really nice. So the preload scanner looks out for things like source and href attributes and their values. Turns out it also looks out for the poster attribute. Complete parallelization behaves virtually identically to image. It is available to the preload scanner. Now, I mentioned that video itself is not considered as your LTP candidate. The only time it would be is if it has a poster image, and even then, it's not the video, it is the poster image. There are sort of rumors, there's murmurings of changing LTP, and I haven't, like not in the last couple of days at least, gone to check this issue, but someone has suggested maybe we should take the first frame of a video as the LTP, which is going to be very, very difficult to do because videos are much slower than images. So what I'd be keen to sort of encourage, if you are using videos as your potential LTP currently, you're probably getting a text-based LTP instead, which is nice and fast. Make sure you're using poster images to sort of placehold that video, because if this change does get implemented, you're likely to see a big drop-off in LTP scores, because the first frame of a video will be a lot slower than the equivalent poster image. Background image is bad. Background image is always going to be bad because of just how the browser works, how CSS works. We've sort of mentioned things like the render tree in a couple of the previous talks this conference. What I did is in the demo, I swapped out the image tag and whatever for a div, and I used an inline style purely because adding an external style sheet would have definitely been a bias. It would have been definitely slower. So I just used an inline style. And this is a really interesting thing. I see this quite a lot. People, as a well-meaning but misguided optimization, embed certain things as inline styles in their HTML because, the browser will discover it faster. You'll see people just pulling their font face declarations out of their main CSS bundle, putting it in the head tag. It's not how it works. We're about to find out how it works. Inline styles that have references to things like background images are not any faster than having it in your external CSS. And we'll find out why in a second. Visualizing this waterfall, again, serialized, complete lack of parallelization. That image wasn't discovered until after the script was finished. This was hidden from the preload scanner. Background image is bad for performance, and if you know anything about how CSS works, this shouldn't come as much as of a surprise. Background images are hidden from the preload scanner. They are what we call late discovered resources. They exist in the same family as fonts. This is a defensive strategy. So if you had a CSS file with 1,000 background images declared in it, the browser's not going to download all 1,000 images. It's going to wait until it knows the page needs it. But it doesn't know the page needs it until the page needs it, which is too late. So when you build a page, you get the DOM and you get the CSS OM, and they get sort of transposed onto one another into the render tree. And it's not until the render tree is constructed that the browser will dispatch requests for web fonts or for background images. Here's a really interesting one. You may see in waterfalls, like somewhere down here, like a random web font gets requested, and you can't work out why. Normally, it's because your cookie banner just got injected with JavaScript. It's got a DOM node that needs a different version of Open Sans, and it gets requested when the DOM node's injected. And a lot of the time, you'll see your background image and your font requests completely divorced from your CSS. That's because CSS doesn't download images or fonts. Your render tree does. And the render tree is the combination of the DOM and the CSS. Basically, background images are more likely to be throttled by your HTML than your CSS, which is kind of crazy when you think about it. The reason these resources, in this specific background images, are slow is because they aren't requested until the browser is ready to paint the DOM node that needs it. And that's way too late. If the browser doesn't know you need an LTP candidate until it's ready to put it on the glass, you're on the back foot. So the takeaway here, not all candidates are born equal. Ideally, a text-based candidate would be the fastest. Statistically, the next most likely is going to be an image. An image is probably also one of the fastest as well when we are about to look at the additional optimizations we can make. And yeah, be aware, if you are using video, or your LTP is likely to be a video, make sure you are using a poster image defensively, just so it's lying dormant in the event that that change does take place. I just want to briefly hit upon some common mistakes. So my work as a consultant means a lot of auditing, a lot of looking at other people's websites. This talk is actually, this could have easily been like a half-day workshop, so I had to cut quite a lot of stuff out. So I've just included my sort of takeaway highlight sort of common mistakes. These are things that I see and I'm like, oh, you could be so much faster if you weren't doing this to yourself, right? It's tragic, it's heartbreaking. This one is just mind-boggling. Not as in this room. In this room, we don't do this. But there's loads of really naive performance advice out there. Lazy loading your images makes your site faster. Yeah, by making your images slower. Asynchronous JavaScript is faster. No, it's not. It's slower. Your site's faster, but the JavaScript... I dealt with this recently. Someone was wondering why they had a really big CLS issue. They had a big layout shift because their nav got transformed into a responsive nav really late. And it's because they deferred and then imported the JavaScript bundle to fix the nav. This is a complete tangent. This has nothing to do with the talk. There's really naive advice on the web. A while ago, the advice was, lazy load your images, it makes your site faster. If you want an image to be fast, don't go lazy loading it. Staggeringly, about 10% of the web currently natively lazy load their LCP, and then the HTTP archivers kind of roughly tried to work out that, given the syntax of the image, an additional 6% are using native, like a naive sort of JavaScript lazy loading. That's even slower, because JavaScript is the fastest way to build a slow website. The syntax for native lazy loading equals lazy, really nice and simple, which is probably why it's so tempting. And this is a really interesting thing that I've had developers ask me. This is a good question, by the way. It's well-meaning. It's a good question. If the browser uses its own heuristics to decide if an image is lazy loaded or not, can't you just stick loading lazy on every image, and the browser will know not to lazy load your LTP? The problem is the browser doesn't know it's an LTP until it's about to render the image, right? So you've got this kind of paradox of it's a bit chicken and egg, right? The browser doesn't know it's the LTP until it's the LTP, which is like, shit, that's way too late. But interestingly, and this is by design, and I think this is very, very elegant, as soon as you put loading equals lazy on an image, it gets hidden from the preload scanner. It's a beautiful bit of design, right? Don't eagerly fetch anything. Wait until the parser encounters it. So you're guaranteed a slow discovery for your image if you put loading lazy on, regardless of even if the browser could do magic around the viewport. If we just stick loading lazy on the exact same LTP candidate, we can see how quickly, or not how quickly, just how obviously, we lose access to the preload scanner. Don't lazy load your LTP, ever. And this one used to break my heart, but it's like now we do know better. And if you're doing this, it's just, at this point, you're just being a bit silly. I've got like a bit of a sort of CSS snippet that I run through like a browser extension that just injects CSS onto pages. When I'm working on a client site, I will enable that extension, and one of the snippets is this, and I'll just bum around their site, clicking around until I see a red image in viewport. It's like, cool, that shouldn't have been lazy loaded. So you can find these, this is relatively manual, because I've still got to click around. You could send Puppeteer through the site, I guess you could send a headless browser through. But this is just a quick way of seeing, has it got loading lazy on it? You could also extend that selector to be like, if it's a JavaScript lazy loading library, you could look for a class of image.loaded or something. Anyway, don't build your LCP in JavaScript. Like I said, JavaScript is a really good way to make a slow website. And a good example of this was BBC iPlayer. This is a client of mine. We worked together sort of late spring this year. iPlayer is like British Netflix. And their site is actually reasonably fast. And basically, they use React on the server. It's all server rendered. Except for some reason, the video player component is all built on the client. Like the static aspect of it. Like the image itself is built on the client. It doesn't need to be at all. What that meant, and when you look at this waterfall, you'll see there are other things we need to optimize as well, but I'm focusing just on image discovery here. To start with, the LCP was built in JavaScript, so we had to fetch this big main bundle. What's annoying is that main bundle is the app, and it's getting very late discovered. I can see on here, it's the 30th request was their main app, right? That's way too late. That's an optimization we need to make. It also wasn't discovered until 4.5 seconds in, right? So we've got other optimizations to make here. But that app is the thing that's actually, or that bundle.js is the thing responsible for building this component on the client. It was really easy to refactor. Well, for them, I didn't do anything. I think I went and got coffee. Told the engineers to refactor this, build it on the server, and the bottom thing we got, it's discovered way quicker. It was discovered as the 17th resource, which is way, way faster. It just made a huge improvement. I think it's about 43% improvement. The next thing to optimize, we're going to come back to, they were hosting this off-site on a first-party, third-party origin. That's a delay that we could do without. You can see quite clearly the day this got implemented. This is very reassuring to see. And honestly, it took the engineers like 90 minutes. It was a really quick job. And yeah, it was a 43% improvement in LCP. We're still going way over budget. But like I said, there's more work to be done. But don't build your LCP in JavaScript in any way, shape, or form, whether that's lazy loading it with JavaScript, whether that's building an entire image gallery in JavaScript. Make sure your LCP candidate is right there in the HTML for early discovery. HTML is fast. So yeah, looping back around to this, don't host offsite. Self-host your LCP. Whether you do that through reverse proxies, I don't care how you manage it, just make sure your LCP stays on the same origin as the page that is displaying it. The best example of this I had was my own mistake a couple of weeks ago. I accidentally nudged my LCP onto Cloudinary, and I love Cloudinary. Cloudinary does a very good job of just picking up the slack. You know, developers, we know to optimize images, we don't. Cloudinary does it for me, and I accidentally nudged my LCP onto Cloudinary. What you can see is that I went from a 2.1 second LCP to 3.5. I've completely overshot that 2.5 second budget. It's a real loss. That's a huge difference. And that's because even though the image was 1.5 times smaller, it took 2.6 times longer to fetch. Because the trip to that other origin just was not worth it. What I actually sort of did is I ran the image through Cloudinary, saved it to my local machine, then deployed it on my own origin. So I got the best of both worlds in the end. But yeah, I accidentally nudged my LCP onto a different origin. Always self-host your static assets. Never, ever leave static, especially if they're in any way critical. Don't leave static assets on anybody else's origin. There is no benefit to doing that. Don't usurp your LCP. I feel very guilty because the usurp's just such a shit word. It's very old-fashioned. It kind of means like to sort of like overthrow. One of the synonyms was dethrone. Don't dethrone your LCP. This one does break my heart because most of the time developers don't know why this is happening. This one's really upsetting. This is a client of mine, and there's quite a lot going on this screenshot. I don't want to sound like a sycophant, but I am a huge, huge fan of SpeedCurve because they spot things that me and my clients just don't. So we got an alert about this. On day one, on the left, we can see what I'm trying to say. Oh yeah, day one on the left, we've got the site as it was. Day two on the right, LCP got 54% worse, right? It went from 8 seconds, which is still not good enough, to 12.5. All right, it got 54% worse. Can anyone just work out what happened here? It's fairly obscure, and there is a lot going on. The middle is just a visual diff, so just ignore the middle for now. Can anyone work out what happened? Right, cookie banner, yeah? Exactly, cookie banner. This is so upsetting. But it's a bit more complex than that. Their CMS, their e-commerce platform, is pretty smart. On day one, the H1 said Cannondale mountain bikes. The LCP area, 46,000 square pixels. They sold, and you can actually see it here, it says one product. They sold the last Cannondale bike. So their CMS automatically just sends them to, and it doesn't redirect them. It just says, well, you can't buy a Cannondale bike, so I'll just show you all mountain bikes. So on day one, the LCP candidate was the H1, 46,000 square pixels. The cookie banner, which is late loaded, 44.5 thousand square pixels. The H1 won. On day two, the late loaded cookie banner, still 44.5 thousand square pixels. The H1's only 33,000. Now here's the problem. Developers on their local machines don't see cookie banners, right? It's usually disabled. Honestly, once you've dismissed the cookie banner once, you don't see it on subsequent visits anyway. So it's actually, but this really breaks my heart because this is a huge, huge sort of like it's off people's radars, and a lot of developers don't find this. This is why SpeedCurve found it and not me. Right, okay, those are common mistakes. These are things that I just find really just upsetting to see. Let's just be a bit more ambitious, right? If we avoid all the mistakes, there are certain things we can do to go the extra mile. And I think, given the audience, this is the stuff that we're more interested in. First thing I want to talk about, you've likely all heard of already. I want to talk about resource hints. Specifically, I want to talk about preload. Just a quick show of hands. Who's used preload before? Yeah, like everyone, of course. Who stopped using preload because it's not very good? It's fine, it's just quirky. So preload is an interesting resource that we can use. Syntax, declarative fetch, really simple. Goes in the head usually, could go in the body, but use these sparingly. The way I talk about preload is it's a queue jump. It only makes the preloaded resource faster because something else had to yield and become slower, right? It's a queue jump. There's no magical button that makes your website. There is actually. It's on the right-hand sidebar of my site. It says Contact Me. That's the magical button that will make your website faster. Preload is a queue jump, right? It doesn't actually, something has to yield, so don't overuse it. Preload is useful for late discovered resources. The clue's in the name. Preload reintroduces resources to the preload scanner. Resources we'd previously hidden, or that were hidden from the preload scanner, can be resurfaced from the HTML by using preload. I generally wouldn't recommend using preload for a resource that's already in the HTML. So if your LCP is an image tag, I generally wouldn't recommend using preload. I'll explain why in a second. But it's useful if your LCP candidate is a background image. I mentioned how background images are really, really slow, because that's just how browsers have to work. My site uses a background image for its LCP, so I had to sidestep the problem of slowness. The top waterfall shows my background image is requested as the fourth resource. It's requested from the body, so here's a pro tip. When you're looking at waterfalls in Chromium, you'll see there's like a two-step loading phase. You've got the head tags and then the body tags. And what you will see is that the CSS is the only thing in the head tag, so it's kind of orphaned. If I had like a few CSS files and a couple of JavaScript files, you might see sort of 5 requests happening at once. But then the body is requested separately. So the Chrome sort of swarms your head tags, requests those. While it's parsing anything in those head tags, it might trickle 1 or 2 lower priority body resources through. If you're lucky, that might be your LCP image. But basically, because this was a background image, it has to get requested from the body because it's attached to a DOM node that's in the body. What's also quite interesting is you'll see it takes 932 milliseconds to download this file because the bandwidth is shared. There are other files in flight at the same time. One interesting thing about H2 and unlimited number of parallel requests is bandwidth doesn't increase. It just dilutes. So one interesting caveat when you start looking at sort of parallelization is that you're not magicking more bandwidth out of thin air. It's just all the files that are in flight have to share the same bandwidth. So what happens is that LTP image took 932 milliseconds because it's sharing bandwidth with a script and another document. As soon as I preloaded this, it got requested from the head. We can see that because it's in flight alongside the CSS, which is a head resource. It's the third resource, not the fourth, and it takes less than half the time, 445 milliseconds it took, because that bandwidth is no longer shared. It's been donated or given exclusively to that image. So not only was the discovery faster, the download was way faster as well because it had exclusive access to the network. That was an 800 millisecond improvement in LCP, which is a huge, huge number. OK, I mentioned it was a bit rude of me. I shouldn't have said it quite how I did. That preload has had some issues, and it needs using very carefully. Used in the right scenarios, preload is very, very powerful, but it can be easily misused. As we saw, like 95% of you have used preload already. If you haven't used preload, before you do, just do me a favor and read this, because I don't want to be responsible for making your site slower. This is a slide from a previous talk that I gave about resource hints, and there are some definite caveats when it comes to using preload. Next thing, and I'm in love with these, is priority hints. Priority hints are amazing. Priority hints, again, a very, very simple syntax. Fetch priority equals whatever, in this case, high. These, again, simple, just an attribute that adds to your HTML. These usually go in the body, but not always. We can use them in the head. Again, use these sparingly. If you make, Andy Davis is in the room somewhere. He coined a phrase. We worked together on a project years ago, and it always stuck with me. If you make everything important, then nothing's important. So you need to use these selectively, use these carefully. Fetch priority high is useful for in-page resources. So you'd normally use these on the image-based LTPs is what I recommend these for. It reduces the amount of time spent queuing. This is the important bit. Fetch priority high will not allow the browser to discover your image any quicker, but it will tell the browser how to handle when it requests that image. And the numbers I'm about to show you blew my mind. It allows us to control priorities. And we just need a brief recap on what priorities are. When a browser loads a page, each resource has an inherent priority. And that is usually how important is this to rendering the page? Is it going to block other resources, X, Y, and Z, et cetera, et cetera? And we've got very, very limited control over what these priorities are. That was until the priority hint spec was introduced. And we actually get to control the priorities of assets that get requested. If you've ever seen this, this is quite an interesting one. You see this, you can see this in Chrome for definite in the protocol monitor, but it's surfaced really nicely in web page test. The initial priority for the LTP image was low, but it changed to high. The browser can change priorities. All images are requested with low priority, but as soon as the browser realizes it's in the viewport, it can and will change that priority to high. Pay close attention to the next screen. There's a little red circle. Look at the middle of that red circle. I'm going to show you an image on a client site that was just a regular image tag without any fetch priority attribute. And I just want you to watch what happens. You see, well, you don't at all. You see where it says queuing on there and it's got an empty white rectangle? They should make your toes curl. This is how long the browser knew the resource existed but did nothing. And the browser's kind of being smart, but we're a bit clever. Well, actually, we're not any cleverer. I've met browser engineers. We aren't cleverer. But we can do things to help the browser act a little faster. Just to pull this out into a bit of more of a static screenshot, that file was discovered and left just sat there queuing for 2.16 seconds. Because it wasn't for 2.16 seconds that the browser realized, oh shit, this is the LTP. Well, it didn't know it was the LTP. It knew it was in viewport. This actually led to an LTP event firing at 13.8 seconds, which is unforgivable. So what I did, just as an experiment, because the reason this is such a late LTP is there's third-party blocking AB libraries, et cetera, et cetera. There's a lot going on here. But what I decided to do is, OK, well, this image is available to the preload scanner. It doesn't matter if the head is blocked. Let's see if I can do something about this. Added this simple attribute and value to the HTML. Watch the same video. I mean, if you blink, you will miss that. To pull it out into a static screenshot, 0.85 milliseconds. Put another way, I was over 2,000 times faster. Mental. That led to an LTP at 4.9 seconds for the sake of one little attribute. I mean, still way over budget, but that's incredible. I need to start hurrying up. Just to pull these out, in fact, you know what, that's just a wall of numbers. The key takeaways are we almost completely removed queuing time, almost completely. LTP was dropped from, oh no, we had nearly a 9-second improvement in LTP for one attribute. Never tell your boss or your client that you'd put an attribute on their image. Just show them a slide like this before you submit your invoice, because you're not going to get paid for an attribute. Last one I want to show you is image decoding. Image decoding is a bit of an odd one, and I feel a bit, I don't know, it's kind of really not very well documented. This is very new, well, it's relatively new, sorry. It's not very well documented, therefore not very widely used. All the documentation is very like lawyer kind of speak. None of the documentation tells you it's good or bad or when you should use it. Nothing advises when you might want to use this. The closest I got was image decoding is said to be synchronous if it prevents presentation of other content until it's finished. The word prevent sounds bad, like, ooh, should avoid this. But if your LTP is an image, maybe you do want to prevent rendering of content around it. So image decoding is a new sort of API. Stick an attribute on an image, we can have decoding async, auto, or sync. If we do a test with decoding equals async, when we run a profile, we get something that looks a bit like this. This is ugly and really, really quite small, so I do apologize. But a few things I want to show you. Just before this, I've got a blue highlighted, like translucent blue. If you look just to the left of that translucent blue, we've got two bits of green task. One says image decode and one says rasterize paint. So we started an image decode event just before this blue. The first frame of change that we see is a slightly decoded bit of image. You can see just a tiny sliver of image slightly decoded at the top. The second frame shows no visual change in the viewport. We've rendered a new frame, but we don't see anything different. Third and final frame shows the LTP is painted. Because this is an asynchronous decode, we told the browser, hey, look, just do other things in and amongst if you want. So we had an image decode event, but then we had this massive recalc style and layout event. Basically, this is a page with 1,000 paragraphs underneath the image. And what we did here is we started rendering the 1,000 paragraphs off screen, useless when we want to optimize LTP. We then, that meant an overall time of 700 milliseconds. The image decode still took as long as it ever would have taken. It's just that we allowed the browser to do other things in between, which we shouldn't have done. Swapping this to decoding equals sync, very, very different story. Decoding equals sync, we see first frame, slight image decode. Second frame, full image decode. Nothing else in between. Looks like a frog. I just noticed that. And this is over twice as fast. Again, keen to stress, the image decode wasn't any faster. It still took as long as it took to decode the image. We just didn't let the browser do anything else in between. So now I'm kind of thinking, maybe this would be a good pattern generally for image-based LTPs. High priority fetch and a synchronous decode. Maybe. I've got a caveat on the last slide where I'm going to tell you to test all of this before you start blaming me for problems. And the flip side, maybe if we put loading equals lazy, we could afford to put decoding async, perhaps. This is a pattern I'm keen to experiment with. I've got very little time left, so luckily we're on a summary. I'll try and just recap what we talked about. LTP is a final metric. It's like the end point. So optimize everything beforehand. Make sure you've solved TTFB. Make sure you've got no silly redirects. Make sure your web application firewall's not tripping you up. Choose the best candidate. Text is best. Image is probably second best. Make sure your LTP is discovered early. We love HTML. Honestly, HTML is super fast. Don't make silly mistakes. Lean on new APIs where they make sense, but if you're going to do that, please test absolutely everything, because with all the goodwill in the world, you could end up making the site slower without testing it properly. With that, I want to say thank you for your time. I think we've got a little bit of time for questions, but yeah, thank you all for listening. That was great. Thank you.
Pull up a chair.
Cheers, man.
A master class right there. So the first thing I'm going to say is this. We're not going to be able to get to every question here. So are you game to answer these on Twitter?
Twitter, around sort of in corridors and stuff.
Okay. Oh, yeah, because we're in person. I forgot that. Let me...
Although you are so weirdly far away from me. Is that deliberate?
I mean, I was told that I have to be like cute for the camera here. So that's why I'm sitting here.
Right, we've got time for one question. I'm wasting it. I'm sorry.
Okay, seriously. So I'm going to get to this one right here because it addresses a couple of things that even I was thinking about. So what if you use loading lazy combined with fetch priority high? Is it still not noticed by the preload scanner?
Oh, God.
Thank you. You'll be unnamed, but thank you.
Well, that's my little task for after this talk. I'm going to find that out. I mean... Hopefully someone's built something into the networking stack that just crashes your browser for even trying that.
Okay. All right.
I've always wanted to do a meme, like the meme of the guy who's like, he doesn't know whether to press that button or that. The superhero is like, do I press this button? I always wanted to put loading equals lazy on one of the buttons and preload on the other.
Yeah.
So I see a lot of that.
Yeah.
But that's a really good question. That's That's chaotic evil, I think.
Oh, man. I mean, we didn't get... Okay, so what about this one? One more? Okay. What are the main reasons CDN hosting for LCP is so much slower? Is it the TCP connection overhead containing the new origin? Does it change with H2?
No. H2, you could do domain... not domain... coalescence. Yeah, so H2, if they're on a different origin but same IP, you may benefit from something called origin connection coalescence. But no, H2 doesn't really change anything.
Okay.
If your LCP is on Cloudinary, you are going to incur TCP overhead, and it's going to be slower. You could try and do a reverse proxy, but that's engineering effort. Just try and self-host your LCP.
Awesome. All right, well, give it up for Harry, please.
Thank you all so much.
That was a fantastic talk.